In this video, we want to look at the concept of average atomic mass, which will finish out our coverage of Chapter 3. First, we want to look at why we have something called average atomic mass and how it is calculated. Average atomic mass is there because on the periodic table, it is listed as the average of all of the different isotopes of a single element. So when we look at the periodic table, the mass that we see is always going to be an average of each type of atom that can exist for that element. There are multiple isotopes for many different atoms. They have different masses, different mass numbers, so we have to report the mass as an average. This has to be done as a weighted average. This isn't your traditional average of, A plus B divided by 2. This is going to be a weighted average because you have more of one substance than you have of another. And we'll see that as we come further into this topic. But since there are many different isotopes with different mass numbers, and remember, it is incredibly crucial that you think through the concept that the mass number is the protons plus neutrons. It's always a whole number, and it is never listed on the periodic table. The only thing listed on the periodic table is the average atomic mass of all of the isotopes that make up that element. The way we discover average atomic mass is we start by figuring out what percentage of what's the percent abundance of each of the isotopes of a single element. So if you have an element that has 2 or 3 isotopes, or 4 or 5, what percentage is made up of each isotope? To do that, we use what's called a mass spectrometer. In a mass spectrometer, you put a sample of the substance into the mass spectrometer on the left side here. So you start over in this area. The sample is entered in there. A beam of ions is shot through the mass spectrometer into a magnetic field. Lighter ions bend more, heavier ions bend less, and the ions that bend the right amount hit the detector. You change the magnetic field, and you can tell how much of each mass isotope is hitting the detector. And from that way, we can find the percent abundance of each isotope. If they were equal, it'd be 50%, but in most cases, there are multiple isotopes with different percentages. So for example, carbon has 3 known isotopes on the Earth. Carbon-12, which is actually 98.89% abundant. Carbon-13, 1.110% abundance. And carbon-14, 0.0001000% abundance. You'll notice these masses are not mass numbers. These are actual masses where you're adding in the mass of the protons, neutrons, and electrons. Mass number is just protons plus neutrons. So when we want to calculate this, we do a weighted average. The way to do a weighted average for carbon, for example, here is to take the 12 AMU and multiply by its percentage. Remember, when you're multiplying by a percentage, we make it a decimal. So 12 times 0.9889 plus 13.0034 times the percentage of that isotope, 0.01110, and 14.0028 times the percentage of that isotope. Add those 3 multiplications together, and you get 12.01 AMU, which is what you find on the periodic table. So the general formula is listed down here at the bottom. The average atomic mass is the sum of, and this symbol here, sigma, means sum of the percent abundance times the mass of the isotope. So let's look at some examples. Element X exists in nature as only 2 isotopes. Element X has an atomic number of 20. The 2 isotopes are X42 and X45. If they were equally abundant, what would be the average? So if they were equally abundant, we'll do average atomic mass equals 42 times 50%, so 0.50, plus 45 times 50%. We would get halfway in between, which would be 43.5 AMU. That would be your traditional average, but in most cases that is not the way that it works. Most of the time it is not a traditional average, it is a weighted average because we don't have an equal amount of each one. So in the second case, the average atomic mass would be the percentage, the mass, 42, times the percentage, 0.9875, plus 45 times 0.0125. Do this on your calculator. The first one, you get 41.475, and you're adding that to 0.5625. I'm going to keep the same number of significant figures here that I had in my percentages. So 3 significant figures in this case, and 4 in this case. So I'll round the significant figures, 41.48 plus 0.563, and end up, now I'm adding, so round to the least number of decimal places, 42.04 AMU. 98% is 42, so it's a very close to 42 average mass. Okay, copper has 2 known isotopes, copper 63 and copper 65. Their masses are 62.9396 AMU and 64.9278 AMU. Copper 63 is 69.09% abundant. We want to find the number of protons, neutrons, and electrons, and the average mass. I would pause here, try this problem yourself, and then press play and see my answer. So in the first case, copper 63. We know copper has 29 protons. So 63 minus 29, or 34 neutrons, and it's neutral, so 29 electrons. Copper 65 has 29 protons still. It has 2 more neutrons, so 36 neutrons, and still 29 electrons. To do the average atomic mass, I need the percent abundance times the mass of each isotope, so 62.9396 times its percentage, 0.6909, plus the mass of the second isotope, 64.9278, plus its percentage. It'll be 100 minus 69.09, since it's the rest of the percentage, so 30.91%, 0.3091. So do the multiplication and round the correct significant digits. For this first one, I get 43.48. The second one, I get 20.07. Add those together, I get 63.55 AMU. Okay, a third example. Oxygen is known to have 3 isotopes. The isotopes are listed here. So in this case, average atomic mass, 15.994946 times 0.99762 plus 16.991315 times 0.000373 plus 17.993584 times 0.00201. The first one, I get 15 point, and we've got 5 significant figures here, 957 plus keep 3 significant figures here, I get 0.00634. For this one, I'm going to keep 3 significant figures, 0.0362. Add these together, 15.957 plus 0.00634 plus 0.0362. keeping 3 decimal places, so 15 point, in this case, if we keep 3 decimal places, 16.000 AMU. Okay, that concludes average atomic mass. We will have more examples of this in your homework.